we need to compute the integral of the x cubed plus 1 over x cubed plus 4 times x squared plus 5x. The first thing I suggest that we do is to add and subtract a few terms to the numerator of this fraction. So we'll go like this. We have integral of x cubed plus 4 times x squared, this is the new term, plus 5 times x. As you can see, I'm forming the expression, exactly the same expression in the numerator that we have in the denominator. But then I have to subtract these two terms I've just added so that nothing would change. So I'm subtracting them. Minus 4 times x squared minus 5x, and I still have plus 1 left. And this all goes divided by x cubed plus 4 times x squared plus 5x dx. Now we can separate this large fraction in two. And we'll have the integral of x cubed plus 4 times x squared plus 5x over x cubed plus 4 times x squared plus 5x, and plus the second fraction, which is negative 4 times squared x minus 5x plus 1 over x cubed plus 4 times x squared plus 5x dx. As we know, the integral of the sum is equal to the sum of the integrals. So we can split this large integral in the sum of two. So we'll have the integral of this first fraction plus the integral of the second fraction. Now, obviously, this first fraction yields 1. So the first integral would be simply x. The second integral remains with no changes. So we have the integral of negative 4 times x squared minus 5x plus plus 1, over x to the third plus 4 times x squared plus 5x dx. Let's rewrite the expression we've obtained in the top. So we have x plus the integral of negative 4 times x squared minus 5x plus 1 over x cubed plus 4 times x squared plus 5x dx. Now we're going to have to compute this new integral we've just obtained. And I suggest that we do that using the partial fraction decomposition method. So our second step is to calculate this new integral. Negative 4 times x squared minus 5x plus 1 over x to the third plus 4 times x squared plus 5x dx. The first thing to do to use this method is to factorize the denominator of this fraction. Obviously, the first thing we can do about it is to factor out the x. Let me write this fraction separately. Or not yet. We'll have the integral of negative 4 times x squared plus minus 5x plus 1 over x times x squared plus 4x plus 5 dx. Let's now check if this quadratic polynomial can be factorized further. To do this, we should pretend as if it is a quadratic equation and solve it. So we're calculating the discriminant, and we go 4 squared minus 4 times 1 times 5, or 16 minus 20, which is equal to negative 4. This means that this equation has no roots, and hence this factor can't be factorized further. And now here comes the method itself. Let me write this fraction separately. Minus 5x plus 1 over x times x squared plus 4x plus 5. This fraction can actually be presented as a sum of the following two: a over x and b times x plus c over x squared plus 4x plus 5. As you can see, each of these fractions has the denominator as the factors in this initial one, and the numerators are 1 degree less than their denominators. Now let's reduce them to the common denominator, and we'll have a times x squared plus 4a times x plus 5a, and then we'll have b times x squared plus c times x over x times x squared plus 4x plus 5. Now let us equate the coefficients standing next to the x's with the same degrees. So we have negative 4, the coefficient standing next to the x squared, is equal to a, coefficient standing next to the first x squared, and then we have b, a plus b. Likewise, we have negative 5 is equal to 4a plus c. And finally we have 1 is equal to 5a. We now have the system of 3 equations, out of which we can calculate these 3 coefficients a, b, and c. So first comes a. A is equal to 1/5. Then we can substitute this value into one of these equations and obtain b and c. So we have b is equal to negative 4 minus a, and a equals 1/5. So we have negative 4 minus 1/5, which is equal to negative 21/5. And then we have c, which is equal to negative 5 minus 4 times a, and a is 1/5. So we have minus 4 times 1/5 which is 4/5, which is equal to negative 29/5. So we can now substitute these coefficients into the fractions. So we have 1/5 over x we have negative 21/5 times x minus 29/5. Or if we factor out 1/5 and put the minus sign in front of the second fraction, we'll have 1/5 times 1 over x minus 21x plus 29 over x squared plus 4x plus 5. Now let's substitute this newly obtained expression into this integral. So we have the integral of 1/5 times 1 over x minus 21x plus 29 over x squared plus 4x plus 5 dx. Let's pull 1/5 out of the integral, so we'll have 1/5 times the integral of the difference 1 over x minus 21x plus 29 over x squared plus 4x plus 5 dx. Now the integral of the difference is equal to the difference of integrals. So we can write it in the following way. 1/5 times the integral of dx over x minus the integral of 21x plus 29 over x squared plus 4x plus 5 dx. Now this first integral is equal to ln of the absolute value of x, and the second one remains with no changes. 21x plus 29 over x squared plus 4x plus 5 dx. Or if we expand, we'll have 1/5 times ln of the absolute value of x plus 1/5 I'm sorry, we had minus here. This is my mistake. So we have 1/5 times ln of the absolute value of x minus 1/5 times the integral of 21x plus 29 over x squared plus 4x plus 5 dx. Let's now put this expression to the top so that we wouldn't forget anything. So this expression is what this integral transformed into. And we can write x plus 1/5 times ln of the absolute value of x and minus 1/5 of the new integral, which is the integral of 21x plus 29 over x squared plus 4x and plus 5 dx. Let's now deal with this new integral. So the integral of, the sign is too small, the integral of 21x plus 29 over x squared plus 4x plus 5 dx can be split in two. So we'll have the integral of 21x over x squared plus 4x plus 5 dx, and plus the second integral, the integral of 29 over x squared plus 4x plus 5 dx. Let's separate the full square out of these denominators, and if we look closely at them, we'll see that it can be written like this: x squared plus 4x plus 4 and plus 1. This expression is the full square of x plus 2. This is the expression that might come in handy, so we're about to use it. Now, one step at a time. We can add and subtract 2 from this x right here. Basically, we've added 0 here, so nothing changed. And this goes divided by x plus 2 to the second power plus 1 dx. Then we have the second integral. Let's pull 29 out of it and we have dx over the x plus 2 squared plus 1. Now let's rewrite the first one unchanged. 21 times x plus 2 minus 2, x plus 2 squared plus 1 dx. And this one is equal to 29 times the inverse tangent of x plus 2. And again, I need more space. Let me mark it for you. Now let's deal with the first integral. I suggest that we separated it as we've already done today. So we'll have 21 times the integral of x plus 2 dx over x plus 2 squared plus 1. Then the other part of the fraction, 21 times 2 times the integral of dx over x plus 2 squared and plus 1. And we don't forget our inverse tangent. So we have plus 29 times the inverse tangent of x plus 2. Now, we can put this expression under the differential, but we need to divide the whole thing by 2. So we have 21 over 2 times the integral of the differential of the x plus 2 squared. As a matter of fact, nothing would change if I add 1 here, over x plus 2 squared plus 1 minus 42, and this integral gives us another inverse tangent of x plus 2, and we already had 29 times the inverse tangent of x plus 2. So we have 21 over 2 times the ln of the absolute value of x plus 2 squared plus 1, which actually is always a positive value, which actually would be always of the positive value, so we could have put the parentheses instead of the absolute value sign, but this is not a mistake as well. And then we'll have minus 13 times the inverse tangent of x plus 2. go straight to the top. So we already had x plus 1/5 times the ln of the absolute value of x minus 1/5 times the integral, which yielded this expression. So let's substitute it into these brackets instead of this integral. So we'll have 21/2 times the ln of the absolute value of x plus 2 squared plus 1 minus 13 times the inverse tangent of x plus 2. And then we'll add the constant of integration. And finally, we have x plus 1/5 times the ln of the absolute value of x minus 21/10 times the ln of the absolute value of x plus 2 squared plus 1 plus 13/5 times the inverse tangent of x plus 2 and plus the constant of integration. So this whole expression is the solution to this red integral.